You have seen this diagram before. It shows that most of the surface of the Earth is either at 800 meters or at around 3.7 kilometers underneath sea level. Less than 10% is higher than 800 meters. Maybe not very much, but still very important. These are the mountains, major features of our planet. Mountains, for instance, are the source of most of the terrestrial sediments we find in sedimentary basins. How do mountains form? In the slide, you see a section across the Alps, a mountain belt where I have also been working for many years. Mountain belts like the Alps are formed by the collision between two lithospheric plates. In our case, these are the European plate in the north and the Adriatic plate in the south. The moho of the European plate deepens towards the south. The moho of the Adriatic plate, on the contrary, deepens towards the north. As a result, the crust underneath the Alps is much thicker than in the surrounding regions. A thick crust is one of the main characteristics of mountain belts. In the mountain belt itself, you see a large number of thrusts, faults which accommodate shortening. Shortening is another characteristic of most mountain belts. We know by now how we can get these mountains. By shortening, the crust becomes thicker, and to reach isostatic equilibrium, the moho deepens and the surface of the Earth moves upward. The hypothesis that topographic creation is associated with shortening is proven by the thrust and by reverse faults in the external parts of the origin. Major shortening takes place at convergent plate boundaries, typically with one plate subducting underneath the other. Rocks of the lower plate are brought towards the convergence zone, indeed an area of strong friction and deformation. Rocks will then be scraped off from the lower plate, piled up, forming an accretionary wedge. A mountain is born. In the slides, you see now a simplified scheme of how a mountain belt forms. At the initial stages of shortening, the orogenic wedge is small and defined by two thrust surfaces with opposite dip. With increasing convergence, the wedge grows because of the mass being transported by the plates and accreted to the origin. Note how the wedge grows but preserves its shape, nicely illustrated by the slopes of the two sides of the origin which do not change their angle. The resultant origin has two very different parts, the frontal and the axial regions. Rocks in the two domains have experienced different paths and will look very different. The two sides we mentioned of the mountain belt are very different. The frontal part is generally wide with gentle slopes. The formation is spread over a large number of shallow dipping thrusts functioning as the fold-bend faults we have seen at an earlier stage. Each thrust accommodates only a limited amount of deformation, it then stops, and its ongoing shortening is accommodated by a new thrust, typically developing in a more external position. As a result, the origin becomes wider. The axial and the back part of the origin, on the contrary, are narrow and have steep slopes. Most of the shortening is accommodated by a few steep faults called back thrusts. Rocks ending up in the frontal regions will never be buried at large depths. They will be deformed when they enter in the collision zone, picked up by thrust, and move back to the surface. As a result, they will not experience high pressures and temperatures and will be broken in fully fragile manner with discrete faults and folds. The axial parts of the mountain belt have very different evolution. Rocks eventually ending in the axial part of the mountain have been brought at depths of up to tens of kilometers, and when they get in the neighborhood of the rigid part of the upper plate, can either subduct deep into the mantle or move upward, ending up in the high mountains. Indeed, if you want to search for metamorphic rocks, you need to go to the high mountains. During these paths, the rocks experience deformation at high temperatures and pressures. This result is very different from what we've seen from the low temperature rocks. Having seen all this, you will surely agree that mountains form a very dynamic system. Rocks carried by their converging plates are accreted to the origin, which starts to grow, and it will grow in a self-similar way as rocks are accreted both in the deep and in the shallow part. Growth of the mountain, however, does not proceed undisturbed. As soon as relief starts being created, rain, wind, and gravity will start their work, first gently, but then becoming increasingly active when the mountains start becoming high and steep. At a certain moment, an equilibrium is reached with the amount of sediments brought into the system being compensated by erosion. Welcome! The mountains we've been building during the last clip have started producing large amounts of sediments. Where will they end up? Places where large thicknesses of sediments are accumulated are called sedimentary basins. These accumulations can be very thick, up to 10 or 12 kilometers, and can form in very different contexts. How can we make space for so much sediments? What are the controlling processes? Sedimentary basins are systems with two components. On the one side, the processes which control the amount of accommodation space available. On the other, the processes which control the amount and type of sediments produced and eventually deposited into the basin. Note that in most sedimentary basins, creation of accommodation space and sediment production are related to different processes which take place in very different, often unrelated regions. Always keep them separated from each other. We will focus now on subsidence. In next modules, we will look at sediment production and deposition. In a previous clip, we've defined the notion of accommodation space as the space where sediments can be deposited and preserved. The most intuitive accommodation space is the water column between the sea level and the sea floor. In the absence of subsidence, the maximum thickness of sediments which can be deposited corresponds to the accommodation space. As sedimentary succession can be orders of magnitude thicker than the accommodation space available each moment, we need processes creating new accommodation space during time. We've called this phenomenon subsidence. Building on Archimedes' principle, we've seen that subsidence can be generated by thinning the crust, which is the light part of the system, and is enhanced by the thickening of the mantle, which is characterized by its high density. Changing thicknesses of the lithospheric component is equivalent to applying an extra load to a plate. Note that the load can be positive if the lithosphere becomes heavier or negative if the lithosphere becomes lighter. The magnitude and width of the accommodation space depends not only on the weight of the load applied, but also on how strong the loaded plate is. This is an effect we did not look to until now. If the loaded plate is very soft, then the new load and the underlying segment will simply sink, and subsidence will be limited to the area where the new load is applied. The resulting sedimentary basin will be very narrow and confined to the same domain. If, however, the substratum of the new load is very strong, then no subsidence whatsoever will take place, and the topography will correspond to the height of the load itself. No sedimentary basin is created. Reality is often between these situations. The load will push downward part of the plate, but because this has a strength, then also adjacent domain will subside, creating new accommodation space, and therefore sedimentary basins. The first type of sedimentary basin we will look at are extensional basins. Here, the accommodation space is created by the extension of the lithosphere. Extensional basins begin forming continental rifts. If extension continues, then the lithosphere becomes so thin that it will break, and eventually leading to the formation of a passive continental margin. Vertical movements in a sedimentary basin can be documented using a subsidence curve, which describes the vertical position of a point during rifting. The blue curve in the slide is a typical subsidence curve in an extensional setting. Before the onset of rifting, not much happens, no faults, and subsidence is limited to non-existent. When extension starts, normal faults will develop, which open extensional basins and coarse crustal thinning. Both concur in creating subsidence. Following rifting, we enter the post-rift stage, when subsidence is controlled by lithospheric cooling. We have seen that the faster the rift, the higher the thermal anomaly and the stronger the post-rift thermal subsidence will be. Very important sedimentary basins also develop in domains with shortening. During shortening, rocks are piled up and form therefore an extra load applied to the underlying lithosphere, which is gray in the picture. If the lithospheric plate has a finer strength, then it will flex downward, create an accommodation space, which might then be filled with sediments, probably derived from the eroding adjacent mountain belt. This is the four-deep basin. In the picture, you see the main elements of four-deep basins: the load, the basin itself, and the loaded plate. The basin which developed has a triangular shape, thickening towards the mountain and pinching out away from it. Here, some final take-home messages. Sedimentary basins are thick accumulation of sediments. A tectonic process is needed to initiate sedimentary basins. Sediment loading does amplify subsidence, but it is unable to keep the machine going. The type and amount of sediments deposited in the basin are conditioned by processing taking place in the source area. Sedimentary basins host resources, and their responsible management is a key to social development.